So I guess we should just try to construct the homotopy. Let's see. Yeah, see, that's the thing, because I was thinking about this earlier. You can't just multiply one of them by t and one of them by 1 minus t, because, I mean, this is taking values in arbitrary topological space, so that doesn't work. There's nothing that's homotopic that we can exploit. So honestly, I'm not sure how you would construct that homotopy, unless you guys have any ideas. And that's why I didn't go over it.
Yeah, it's okay.
But that's what you would have to show.
Homework for next class.
Okay, so we'll leave that as a open question for next class. That's good.
Yeah.
You can go on
Yeah.
from there then. That's cool.
Open.
Yeah, you definitely have the next meeting, because we
Yeah.
still have
A lot.
many interesting things to talk about in here, and that's fine. You know, I made a schedule, but do the best we can with it. Schedules are made to be broken. Yeah.
Alright, so let x naught in space x, and oh, this is going to be, I guess I'll have to be careful to make my big x's look different from my little x's. It's going to be hard for me. And let big X naught be path component
Theorem 3.5.
of X containing X naught. Then pi 1 of big X naught comma X naught is equal to pi 1 big X comma X naught. So essentially that
Yeah, the same fun.
you can, without loss of generality, think of fundamental group in terms of what path component you're in. You don't have to consider the whole space. So proof. This is one that I at least think I understand. So they let J, oh, that's horrible, X. J here is this inclusion from the path component to the whole space. So essentially what we're going to do in this proof is we want to show that J is in fact an isomorphism between these two groups. So our first order of business is to show it's injective. So one way of doing that is show that the kernel is trivial. So they say if this path class is in the kernel of the induced map, then we have J of F homotopic to some constant, rel I. And that's because, by definition, J star of F is equal to the path class of J of F, right?
Realized what it is that's bugging me.
Right.
I'm an idiot.
And so, if F is in the kernel of this, this is equal to 0, aka in our context,
Okay.
just the path class of a constant map. So specifically here, if you wanted to, you could actually say, this is IP, right?
Just don't say it around my kids.
IP. Ah, I see.
Sorry.
Alright, so
hmm.
let's see.
So the kernel of the induced map, eh?
They also make a claim here. Well, if
That's what.
f is a homotopy of that type, then f of 0, 0 is x naught, they claim. So, let's see.
So your goal at the moment is to show the only thing in the kernel.
Oh, actually, they say this here is the constant map at x naught. That's important, right?
Yeah. Right.
And so from that, they have that f of 0, 0 is f of x naught. So then, since f of I cross I, path connected, and you have a value in x naught, it follows that the image under the homotopy of I cross I is contained in the path component of x naught.
Oh yeah.
So now they say it is a simple matter to see that f is no homotopic in x naught. That's because since the image of this is contained in x naught, strictly speaking, this map here is a function from I cross I to x. But because the image is actually contained in x naught, we can also view this as a map from I cross I to big X naught. And because this is just the inclusion of f, this is, instead of being a homotopy of the inclusion of f to the constant map, just a homotopy of f with constant map at x naught.
Right.
Rel I. So, it being null homotopic shows us that the kernel is trivial because we assumed f was in the kernel, right? And f homotopic to the constant map means the pass class of f is actually equal to the pass class, I need some water, of I sub x naught. So that implies that the kernel of the induced map of J is just the pass class of I sub x naught.
Excuse me.
Which then implies that this is injective.
Right.
So now we just need to show that it's also surjective. So, I mean, essentially, this being surjective is pretty intuitive, right? We have J star is a map from pi 1, big X naught, to pi 1, big X naught. So, no, wait, I think I have, that should be the other way around, right?
I don't think so.
Yeah. This is the inclusion. So, oh, okay. So, I'll go back to pictures now.
So what are the, again? What are the elements?
Now I can use
What are-
pictures to my advantage.
What are the elements of pi 1 of x, comma x naught? What are those intuitively? Like, what is that?
They're going to be loops, essentially, right? They're
Like-
closed paths
So I guess,
in this path component.
to be honest, they're equivalence classes of loops, right?
Right.
Or an equivalence class of a given loop.
You know, like if this is another component,
Yeah. Right.
it's not possible for... everything in here is going to be in here, right? Because it's not possible, for example, to have something like this because they're paths.
Right.
So very clearly you can get everything in here, and it's not going to extend to any other path components.
Mm-hmm.
So from that you can see J star is surjective. Therefore, J star is witness to the isomorphism between pi 1 of x naught at the point x naught and pi 1 of x at the point x naught. Let's see. We're almost out of time. I don't know what else I can cover, but I'll look in a second here. Oh, I guess does that make sense before I erase the rest of it? Okay. We end at 5:30 or 5:35? Was it
3:30 or
3:30? Yeah.
I guess
Okay.
If you want to, you can. I think you probably have time to cover
3.6.
3.6.
Let's see.
I've gotten so I
Oh
can.
yeah,
I've gotten so I can set
that
up.
one's pretty straightforward.
If I leave at 5:35, I can still set up Calc 2. I'm cool. So
Okay.
no problem.
So theorem 3.6.
About 7 minutes.
3.6. So this one kind of builds on the last one, or at least it's a similar theme anyway. If x is path connected, and x naught and x1 are in x, and pi 1 of x at x naught is isomorphic to pi 1 of x at x1. So actually how I think it's easier to interpret this, if you're in any space, or I guess it would be a corollary of this, if you're in any space and x naught
And same path component.
are in the same path component, then you have the same fundamental group. So proof of this. Let's see.
You gotta draw the picture.
The picture. What picture? I think you're thinking of the one after theorem, or just the remarks after theorem 3.6.
No.
That.
No.
What picture?
There's a picture that has to be drawn here.
Are you talking about this?
No.
No.
Oh, just.
You can prove this by picture.
Oh.
So like, what you're about to do is gamma inverse, right?
Right.
And so you can take any loop here, and then
Right, yeah.
it becomes a loop over there, because you.
Right.
Sorry. Every once in a while I remember something.
So that map,
I'm shocked he doesn't have that picture in here.
phi, pi 1,
It looks like Squidward.
x naught to pi 1 x.
Sorry, Nathan.
That's fine.
I'll behave. No, I won't.
Fine.
Try them.
If you pardon me, I'm going to use some computer science notation.
No. Do something.
So, let's see, I guess, yeah. If you have that of past class of F, how do we define it? Oh, I guess I don't have to use computer science notation here. Never mind, I lied.
Huh.
There's somewhere I wanted to, though.
That's
I
cool.
remember when I was preparing for this. Maybe
So
it's later, so I
so
can
you
show you
actually-
guys next time.
So he actually does this calculation in the groupoid here.
Right.
Yeah.
So essentially what you just did,
Huh.
gamma inverse. Well, I guess yours is kind of backwards from this, but
Sorry.
gamma F gamma inverse, right? That's actually the inverse map. So I mean, it's just a different picture, but the same concept applies. And
So phi is
let's see, these are
phi is a group
group homomorphisms. And well, I mean, it's conjugation, so I-421 group isomorphisms.
These are groupoid isomorphisms, aren't they, though?
No, because you pick a base point. We're dealing with the fundamental group.
You're doing multiplication.
See, that's the thing. Like, they define the groupoid,
Interesting.
then they never actually use it. They go immediately to
No,
using
but-
the fundamental
You
group.
use it to show that like exists, I guess.
Yeah, but then
And
immediately
it's
after
just a
that,
group
they say
of
if you pick a
both
base
of
point,
them.
it's a group because
He
you
says
get-
note that the multiplication occurs in the groupoid of X, though.
Yeah, to show that.
Well,
it's,
I
like,
mean,
that
that's
it's
true,
well
though.
defined, I think.
So the
But
formula, well, the formula uses the groupoid, but the target space and the domain are
Right.
groups.
It's a group, yeah.
well, I mean,
Yes.
sorry, being Soprano here. Both of these are contained in the groupoid.
Okay.
So, yes, these are groupoid calculations,
Yeah.
but they're also fundamental group calculations because they're both
In a
contained
groupoid,
in
yeah.
the groupoid. And there you go.
Basically right.
So therefore, I1 of x.
Well, I guess the point is those triple things you have, the bracket, 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 those have different alpha and omegas.
Right. Yeah. One.
So that's why it's in the group.
Oh, right. Yeah,
That's all.
that's
It's not
true.
a terribly deep thing.
Yeah.
But so with that, we reach the beginning of this lecture.
Yeah. Thank you. Then after this comes the fun stuff.
Yeah, actually, the rest of this chapter is really where we start to see Homotopy saying things that are kind of surprising.
Yeah, this actually at the end of the chapter here, theorem 3.19, is where you actually prove the fundamental theorem of
Yeah,
algebra.
a more geometric algebraic topology course would probably spend like several weeks on the rest of this chapter, you know, because it really has more to do with the interface between like algebraic topology and complex analysis or other places where
Yeah,
like the two-dimensional topology and winding number and all that, it's all intertwined.
yeah, actually, it's interesting because a lot of the things they do at the first part of the next section, I think pretty much you could just use complex analysis if you wanted to, whereas they just use straight up topology.
Cool.